Okay, so yeah, let's move the switch to A. We fully charge the capacitor, and then we flip it to B. And so basically just going around this loop, you can say like the sum of these voltages has to equal 0. And again, yeah, some are going to be positive, some are going to be negative. Yeah, let's look at it in terms of conservation of energy. That might be a better way to set this up. So let's look at the rate of change of energy. So energy is going to be, the battery is removed from the circuit. So like when we flip the switch to B, or when we had the switch at A, the capacitor was fully charged. And then we flip the switch to B, we get that oscillation like before, but now the resistor is dissipating energy. And so we should expect the current to actually die off. It should oscillate back and forth, but the amplitude should be decreasing. So that's what we should kind of expect to happen. If we were to graph it, like say the current, we might expect the current to do this and just keep getting smaller and smaller because the resistor is dissipating energy continuously. As long as there's a current, we're losing energy. So eventually the current's going to completely die. Okay, so let's look at this in terms of energy. And so let's look at it in terms of like rates of change of energy. If we take everything into account, let's do this. dE dt is 0, where E is the total energy. But that, I say energy is being dissipated. A lot of it's being converted into heat. So, this will include the heat energy as well. But the current is what's going to die off. So eventually we'll have heat. In some cases, you could have significant radiation as well, either due to just directly electromagnetic radiation from the oscillating currents, talk about that next semester, or just heat itself, thermal radiation. Like if you heat up a resistor enough, it'll glow and give off noticeable amounts of energy. Okay, but anyways, we have all these terms here. Like for the capacitor, we have 3 terms here. For the resistor, we have this I squared R. For the inductor, the we have the energy in the inductor is 1/2 Li squared. So the rate that energy is changing in the inductor, we just take the time derivative of that. And then we have this takes everything into account. So like this is the rate that energy is leaving the system. These two, now I have to think about the plus and minus signs though. These two, if there is no resistance, these two should just add up to 0. That's just energy changing. So maybe I should write this a little differently. Not sure if we need a minus sign here or not. I think we can go with this. Let's take these derivatives. So I want to set up the equation first. And then it's a question of whether or not we want to solve this. So this next term, du b dt, we're taking the derivative of this with respect to time. So the I squared, that cancels we bring the 2 down, that cancels out the 1/2. So we have Li di dt. And then the next term, the derivative of q squared is 2q, so that the 2's will cancel out. So we have q over c times dq dt equals 0. And I want to do a few things here. First, let's factor out an I. And I want to write this term first. So if we take the I out, we have L di dt, that's the second derivative of charge with respect to time. Now this term I'm going to write as R, we have I squared, but we took 1 I out. So that's Q dot. And then this term, we factored the I out, that's this part. So we have something kind of similar to what we had before. What we've had before is exactly this without the R term. So if we set R equal to 0, we get exactly what we had for the LC circuit, which we should. But now to take the resistance into account, and again, the current is something that's going to look like this. Well, invert it because of the way I drew it. It's going to start out going in the negative, counterclockwise direction, where the battery forms, the clockwise current. So just basically flip this picture upside down, but clearly that's not identically equal to 0. It will be 0 at certain times. But yeah, so in order for this equation to be true, we have to have this result. Okay. Oh yeah, so that is the differential equation that we have to solve. Now, I think what I want to do is just write down the answer in this case. And the reason why is just time. Now, you can do this. So I think what I'll do is, after class is over, I think I'm going to just, write this equation down and solve it without, just solve the differential equation. It's kind of fun to do, but it takes quite a bit of algebra to do that, and it will take some time. Actually, maybe it won't take too long. Let's actually do it. So I'm going to write down the differential equation. Hopefully it won't take more than like 10 minutes at the most. If it takes too long, then I'll just record a separate video. But this is the equation that we want to solve. And I'm actually going to erase the board. I'll erase this part. Maybe I'll erase this circuit later. I feel like we're going to need some room. But we want to solve this. And so what I'm going to do is, it's kind of a nice way we can build up the solution. Let's start by saying Q is equal to E to the AT. That's always a good guess to start with. And again, this is a very well-known differential equation. It's a second order. We have two derivatives. So it's kind of a nice little trick we can do to solve this. We can kind of make it an algebraic problem. So anyways, just say, let's start with Q equals e to the AT. Then the first derivative, or a derivative of e to the x is just e to the x. So the first derivative is going to be e to the AT, but then we have to apply the chain rule and bring out an a. And then the second derivative, we take the derivative again, we bring down another a. And so let's plug this into the equation. This, but we're not, I'm trying to think if we want to, let's just plug this in. Now, the thing is, you can multiply, Q by, you can put a constant in front. I think we'll just take care of all of that at the end. So let's plug this in. And what we have then is L A squared e to the AT plus R times Q dot, which is RA e to the AT, plus 1 over C times Q, which is e to the AT. I'm going to erase this. We can always draw the circuit if we need to later. So now we can factor the e to the AT out, or let's just divide by e to the AT. And we can do that because, like e to the, whatever power, that's not going to be equal to 0. So we don't have to worry about that. So basically we have an algebraic equation here. LA squared plus RA plus 1 over C equals 0. That's just a quadratic equation. See, we don't know what A is right now, but now we can write A in terms of all of this. So just the solution to the quadratic equation, you have like AX squared plus BX plus C equals 0. Again, it's maybe a little confusing because our variable now is A. And we do have a C, but it's in the denominator. So anyway, the solution to this equation, instead of x equals, A is our variable. So we have minus the middle term, that would be minus R, plus or minus R squared minus 4L over C, square root of that, the whole thing divided by 2L. So again, you can just look up the quadratic equation. And I just want to play around with this a little bit. I think I'll wind up erasing it later. Let's put this 2L under the square root. So what we would have is R over 2L in parentheses squared minus 4L over C. But then we're dividing by, put it under the square root, we have to square it. So this would be 4L squared. So the 4's cancel out, one of the L's cancels out. Let's do this. So here we have 1 over LC. Might look familiar, that like oscillating circuit, that's at omega. And yeah, so we have two answers for A. One positive and one negative. So maybe we should give some names to these variables. Actually, I want to check the solution to see if that'll help in deciding. Yeah, just in terms of, yeah, nothing really is helping there. So anyways, let's at least give a name to like R over 2L and 1 over LC. Those might make us able to write this a little bit easier. Let's call them alpha and beta. So let's say alpha is equal to R over 2L. Actually, let's call this omega squared. Because omega squared, 1 over LC. So why do we do that? So we can kind of clean this up a little bit. Then we have A would be minus alpha plus or minus. Now I'm going to do something kind of strange here. So let's put a minus sign in front. So here we have omega squared. So again, minus omega squared, that's at minus 1 over LC. And now this term, that would be alpha squared. Okay. And one more thing I want to do. We can write this, the square root of this negative here. We can, square root of -1 is just the imaginary number I. This is not current, that's the imaginary number. Okay, so and I'm going to erase most of this. Just like from here to here. Basically, we just took the quadratic equation to solve for A. Got our two answers, but we gave these terms that pop up names to make them a little more compact. And then for a strange reason, or it might seem strange now, we flip these around and put an I in front for the imaginary number. That'll be useful in a little bit. So anyways, I'm going to erase this and just write the result. So this was A. And there's two answers, so I'm going to call them A1 and A2. So A1 is minus alpha plus I times the square root of omega squared minus alpha squared. And A2 is minus alpha minus. Okay. So now let's kind of go back to the beginning, where Q is equal to A to the E to the AT. And then we have two possible values for A that will make this equation. If we pick the right value for A, it will solve this equation. Remember, we can also put a constant in front. That'll be the very last thing that we worry about, though. And so what you do, we have two possible solutions. And so we can write Q as a sum of those solutions. So we can say that E to the A1t plus E to the A2t. So again, if each of these is individually a solution, then the sum has to be a solution as well, just because this is a linear equation. So for now, this will be our solution. It's dimensionless. We're gonna have to throw a constant in front later, but let's just do that at the very end. And we can actually write this in a rather nice form now, because here we have like e to the a1t. I'm going to write it like this: e to the minus alpha times e to the I omega. Here, then we have omega squared minus alpha squared. So again, when you have like the same base, you just add the exponents. So we can break this up into pieces. And then the second piece, we're going to have plus e to the a2 alpha. Well, that's going to start out the same way. We're going to have this e to the minus alpha, so we can factor that out. Okay, so this might be looking horrible, but it'll actually turn out to be pretty reasonable. I might have to introduce something that I'm not sure if you've seen it before, but there's a very, very important equation. This is Euler's equation. He came up with this, where e to the ix is equal to cosine of x plus I times the sine of x. So one of the most important equations in math and in physics. And so again, if you haven't seen it before, this is due to Euler, one of the greatest mathematicians of all time. And we're going to use that. So what about e to the minus ix? Well, this is e to the I to the power, or e to the I times minus x. So we'd have cosine of minus x. But remember, cosine of minus x is just cosine of x. But sine of minus x is minus sine of x. And so what we're going to do is let's add these two results. Let's just add these equations. So we have e to the ix plus e to the minus ix. That's equal to 2 cosine x. And the imaginary parts cancel out. And so here, that's what we have here is e to the I, let's just call that x, plus e to the minus ix. So this whole thing in parentheses, this is just 2 cosine of omega squared minus alpha squared. So we're actually getting a somewhat nicer result. And what I'm going to do is completely ignore this 2. Because remember, we can multiply by any constant and still have a solution. So our final solution for Q, we can take the 2 out, who cares? We have Q max, because, cosine, I think I did make one mistake. There's supposed to be a t involved here. So yeah, we had like a1 times t. We have alpha t plus this times t. I forgot to write down the t. So anyways, we have q is q max times e to the minus alpha. So e to the minus r over 2l. And then we have cosine. I'm going to see how it's written in the book. The book writes it like this, where omega d is the square root of omega squared, which is 1 over LC, minus alpha squared, which would be R over 2L squared, and then we take the square root. So like this is the solution. It took a little longer than I wanted it to, but so Q is Q max e to the minus R over 2L times cosine of this frequency times T, where that frequency depends on the inductor, capacitor, and resistor. Okay, so a bit of work to get there, but if you can do it, why not? So any questions on this RLC circuit? Again, you definitely don't have to derive this. If you need it, that'll be on the equation sheet. The solution to the RLC circuit. And again, like if you come across this on the homework, just look it up. You will come across this on the homework. So now I erased what it should look like, but yeah, just because we needed the space. Oh wait, right, A1T. I keep forgetting to put these T's. Sorry, that should be yeah, there should have been this e to the minus R over 2LT. And so again, if we look at the charge on the capacitor, normally the charge on the capacitor, if we had no resistance, let me kind of just redraw the relevant circuit here. That's a horrible picture, but so yeah, we have a switch to charge the capacitor. But again, if there is no resistance, once we have this capacitor charged and let it go, this energy, the charge is just going to keep on flowing back and forth. And so if we want the charge as a function of time, it should look like a cosine curve. If there was no resistance, we would just get a cosine curve. I don't want to draw it yet, but what effect would we expect the resistance to have? Well, the amplitude should just decrease. So it should look like this if there's a resistance involved. So we start out with maximum charge. And again, if R was 0, this would just be a cosine curve where every peak would go back to its original value. But because we're dissipating energy, the charge and the current are both going to dissipate. And so this here is this exponential decay, where the greater the resistance is, the more quickly it's going to decay. So this answer makes sense. We have, as time goes on, we have a minus sign in front. So as time goes on, this factor is going to get smaller. So the cosine is just the oscillating part. This part just makes the amplitude decrease and eventually go to 0. All right, so that's an RLC circuit. So I think what I want to do is maybe do a problem involving an RLC circuit, and then we'll take a break and move on to AC circuits. But are there any questions on just getting here? Okay, so see if I can find a problem involving an RLC circuit. I'll just make one up. Yeah, I'll just make something up. Write down what we need here. I'll draw our original circuit on the board again. So we have this loop here to charge the capacitor. Okay, so what we know, let's write down the solution then for Q as a function of time. Q max is C epsilon. And then we have this decaying part. And we have to write down that angular frequency, which is that. So I make up some values here. Let's say the resistor is 90 ohms. The inductor is 61 millihenries. And the capacitor is 45 microfarads. So energy is going to oscillate just like before, except it's decaying this time. So let's find the frequency of oscillations in this circuit. So yeah, we fully charge it, and then we flip the switch to position B. So being fully charged, Q max will be C epsilon, where epsilon is the battery voltage. And let's look at, say, one period. So like the charge starts out, it's fully charged. So how long is it going to take for like one cycle? So like what is the period? And then what's going to happen to, like, how much charge is going to be left after one cycle? So let's so like we have initial charge as C epsilon. And then, charge is going to flow, reverse polarity, and then flow back. But we'll have less charge, after it completes a cycle because of the resistance dissipating some of that energy. So let's figure out, like, what percentage did we lose in one cycle? So, the percentage that we lost. That would be like the change. So if we want to like how much charge we lost in that one cycle, that would be the difference. So QT minus QM divided by what we started with. So like the change over one period divided by what we started with. So to begin with, let's calculate these two terms. So 1 over LC. That's just like before the part with no resistance. So yeah, if the resistance was 0, that would be the angular frequency of oscillation. But now we have to like make a correction to that. So we have 1/61 millihenries. And then the capacitance is 45 microfarads, or sorry, micro is 10 to the 6. And there were 3 conversion factors I remember. Let's start with Henry. Henry times an amp is a volt times a second. And a coulomb is equal to a farad times a volt. And an amp times a second is a coulomb. So this will give us inverse seconds squared. And then we'll take, we'll eventually take the square root to get inverse seconds. So, but let's just do this. Let's use 61 times 45. That's 2,745. So let's do just like we did before. So here we have 10 to the 9. And now I want to break that up in a way that we can take the square root easily. Maybe I'll have to change that, but let's just do this for now. So, won't be in scientific notation. It'll be easier to take the square root. So this is 36.4 radians per second squared. Let's just do that. Okay. Now, the next term we want to find is R over 2L. So we have 90 ohms. 2L, that'd be 122 millihenries. Convert that 10 to the third millihenries per henries. And then we want to get the same units as, we should get inverse seconds here. This is inverse seconds squared. R over 2L should be inverse seconds because then we'll square it. So these have to have the same units, those two terms. So we should just get inverse seconds here. So Henry times an amp is a volt times a second, and a volt is an amp times an ohm. So let me just check the units and then I'll erase it. We have ohms times millihenries, henries, amps, and volts. At the bottom, millihenries, henries, volts, seconds, amps, and ohms. So we get inverse seconds. So numerically, I think I made up the wrong numbers here. Yeah, that's a problem with just making up problems. I made the inductance too high because we're actually going to get a negative number here. And what that means, yeah, I should have thought of this before that was a possibility. With these numbers, it's like basically it's not even going to really oscillate because we have that negative number. So that is a possibility I should have considered. So I want to see how I can change the numbers in a way that will fix that. we can make a smaller resistance. That would be one way to potentially fix that. Or a larger inductance. The larger the inductance, the more it's going to want to, keep driving the circuit. Yeah, let's change the inductance. I want to make sure that I make it big enough. So sorry about that. I'm going to check this and see if this number works. Let's say we change the inductance to 2.1 henries. So that's a much larger because we were in millihenries before. So all this on the board. This will make things much easier to calculate. Oh, here, let's just 45 times 2.1, 94.5. So again, 10 to the 6, we'll do it 10 to the 4th times 100. This is about 106. Oh, I wonder if, I think last time I might have screwed up that calculation and forgot the 10 to the 4th power. So I wonder if the number was actually okay before. Well, let's go with these numbers anyways. Yeah, I think I forgot because we had a 10 to the 4th power here. I think I forgot that entirely. But anyways, I already changed the number, so let's go with this now. So this is 94.5, or sorry, 106, and then times 100 per second squared. Now R over 2L, let's change that number. This would be 4.2 henries. We can get rid of this conversion factor entirely. We save some room as well. Henry times amp over volt times a second. Okay, so 90 over 4.2. That's going to be 21.4. Oh yeah, the units here were per second. And now we can find omega d. So we have 1 over LC. Yeah, let's just do this. See if I can cram this in here. R over 2L squared. So let's see, 21.4 squared, 458. Okay, so yeah, probably made the inductance too large now, but yeah, it makes the resistor kind of insignificant with these numbers. Should have just left it alone. I think I just missed that other factor there. But yeah, so we have 10,600 minus 458. That's 10,142. So basically, taking the square root works out to be about 101 radians per second. And so the frequency is omega divided by 2 pi. So let's divide by 2 pi. So I'm getting a frequency of about 16 hertz. So it's going back and forth, 16 times per second. Now the period is 1/16 hertz then. This was 450. Here, we don't need that anymore. All right, so 1/16, that's like 6, or well, 0.06. So the time it takes to complete one cycle is 0.06 seconds. So that would be one period. And then again, if you look at omega d times t, you have 101 radians per second times 0.06. And basically we get 2 pi. I get 6.31, but 2 pi is about 6.28, but that's just because of rounding errors. This product, omega d times t, should be exactly 2 pi. Cosine of 2 pi is 1. So we're back to, after one period, we have our capacitors fully charged again, but it's going to be a smaller charge this time. So let's find Q after one period. Like how much charge is left. Actually, let's do C epsilon. Let's do Q max is C epsilon. Let's see how much charge we started with. That'll be 45 microfarads times, say it's a 9-volt battery. So 45 times 9 is 405. And a farad times a volt is a joule. And so, we have this micro here. So we have 405 microjoules. Now, let's find out what we have after one period. We have Q max. So again, we have e to the minus r over 2lt. So r over 2l, apparently I erased a little too much. Let's do that again. 90 divided by 4.2. That was 21.4 per second. So if we plug in 21.4 times 0.06, we have e to the minus 1.29. And this cosine term is just 1, so we don't have to write anything down for that. So, we have QT, we're plugging in one period. We have C epsilon, that's that Q max we calculated. So, we did R over 2L is 21.4 times 0.06. That's about 1.29 with a minus sign in front. So let's do e to the minus 1.29. That's about 0.275. Let's say 0.28. So yeah, this is actually going to decay fairly quickly because after one period, 72% of the charge is gone. So yeah, this will be a rather quick decay. So it wouldn't oscillate around too many times before it just stopped. All the energy was dissipated. So again, we fully charge the capacitor, we put energy into the system, we flip the switch, and it would go through a couple very quick cycles, not too many cycles, before all the energy would essentially be gone. And yeah, like even after just one cycle, most of the energy would be gone. Like 72% would be gone. And yeah, maybe like 2 or 3 cycles, it would essentially, all that energy that we put into it would have been converted into heat in the resistor. All right, so any questions on RLC circuits? Okay, I'm gonna stop recording this one.